Hello, my name is Arash Nemati. I'm working in DTU Energy, and today I'm going to talk about one of the applications of the solid oxide fuel cells and one of the most interesting fuels, which is ammonia, and the application of ammonia in this kind of technology. So the first question is why ammonia? So first of all, it's a carbon-free fuel, so it doesn't have any carbon in its molecule. Its storage and transport is much easier than hydrogen. It's less flammable than hydrogen. It cannot burn by itself in the ambient conditions, and it's available for a long time. The ships transported ammonia for different countries, and we have infrastructures to transport it all over the world. So is it easy to build an ammonia fuel SOFC system? The answer is not. It's not that straightforward. So we have some challenges that we want to tackle here in DTU Energy. How to find the problem and how to solve it. We have different levels for this kind of technology. The material level, cell level, stack level, and finally system level. So for testing, we have facilities in DTU Energy for the material, cell, and the stack level. And for the system level, we have a collaboration with industrial partner. And for the modeling part, we can cover all of the scales in DTU Energy, which I will talk today about that, how we done this, and how this helped us to promote this technology. So about the material level, the first question is that how ammonia cracks inside the cell, because this kind of cells use hydrogen as a fuel. So first we need to crack ammonia, which is NH3, to hydrogen, and then we can use that as a fuel. So we have catalyst layer inside the cell in the anode, which is a nickel YZ layer, and this nickel is a very nice catalyst for cracking of the ammonia. So we want to see how fast this cracking happens and how to simulate it. For this, we have this test setup. We have a U-tube reactor that we put some catalyst at the bottom, and we can measure the cracking rate of the ammonia at very different conditions, different flow rates, temperature, species distribution. We can model this and validate our model with the experimental data, and finally we can develop the reaction kinetics for this ammonia cracking. We can do it for novel catalysts, and we can do it for the cells materials that we have in the DTU Energy. So after having this information about the material level, we want to see how ammonia fuel operates at cell level. So we have these test facilities in DTU Energy to do the measurements on the cells for different fuels such as ammonia, hydrogen, and we used multiphysics modeling for modeling of this kind of cell. We are able to validate our results for the temperature distribution. We measured around 8 to 10 Celsius temperature reduction because of this endothermic cracking of the ammonia. And in here you can see that we can validate the IV curves very well for both pre-cracked ammonia, which means that we have an external cracker and we cracked ammonia into hydrogen and nitrogen and send it to the cell, and also for direct ammonia in the right hand side that we directly insert the ammonia inside the cell. We have two important phenomena in the direct ammonia SOFCs. One of them is anode off gas recirculation. Because we don't use all of the fuel in one single pass in the stack, we like to recirculate it, to reuse it, and to use more fuel before sending out to the ambient. So we try to recirculate this unused hydrogen or unused fuel inside the cell. So we performed some tests in DTU Energy by having different levels of the recirculation, 70%, 85% and 90%, which means that we recirculate 90% of the hydrogen again inside the cell and reuse it. And in here you can see that our model can capture it very well, and when we compare it to the experimental data, and in this table you can see how efficient is that. So we can have a very large saving in the fuel, for example, around 22 to 27% fuel saving by this recirculation, and we don't lose that much power by this recirculation. So the next question is that does this direct ammonia produces more degradation sources or any extra problem? And the answer is yes. In the direct ammonia, as you can see, this ammonia leads to some morphology changes and some porosity in the nickel mesh. However, in the pre-cracked ammonia, which is the combination of nitrogen and hydrogen, it doesn't occur. So this morphology change is problematic, especially in the metallic parts like interconnect, that may lead to some cracks and mixing of the fuel and oxygen, and it leads to killing of the stack. So we try to model this phenomena in the cell level, and in here you can see some green arrows that shows the location of the nitriding at different temperatures. As you can see, in the low temperature, it's really problematic. We have this nitriding in the fuel inlet and in the outlet. But in the higher temperature, we see only in the inlet and not at the outlet. You can see our model can qualitatively capture this phenomena. So for both temperature 650 and 750, we can observe the nitriding at the inlet. And also, it can capture how this happens in the outlet of the cell for the low temperature and the high temperature. As you can see, for the low temperature, we have nitriding at the outlet, but for the high temperature, we don't have the nitriding at the outlet, which shows our ammonia is already cracked before reaching to the outlet of the cell. So after having knowledge in the material levels, how to develop the reaction kinetics for ammonia cracking, and for cell levels to understand how cell performs with the direct and pre-cracked ammonia, how recirculation affects the performance, how nitriding affects the performance, we want to transfer this model and this understanding to the stack level. In here we use an approach which we call homogenization approach to solve the stack in a reasonably time. And as you can see in here, we use this method for different commercial stacks, and this method operates very well. So what's the effect of operating temperature and pre-cracking ratio? We want to answer this question, which is one of the challenging questions for the ammonia SOFC stacks. We tried two kind of cell technologies. One of them is low temperature cells, which is alcogen cells. They operate at the temperature between 600 to 700, and one of them is the cells that we have in DTU, which they are designed for the higher temperature to operate between 700 to 800. And we use the same stacks for both of them. We tried different cracking ratios between 0% to 100%. It means that this ammonia that we have, we cracked already 20%, 40 or 60, 80 or 100% outside the stack. And we want to see what's the effect of this on the performance. So one observation that you can see also in this model, if we want to operate our cells in the range that we have defined for them, we should control the inlet temperature and airflow rate. We should control the inlet temperature to don't let our minimum temperature goes beyond the limit, because this ammonia cracking is endothermic and it leads to temperature reduction. As you can see In here at the inlet, we have a large temperature reduction due to ammonia cracking. And we should also control the airflow rate to don't let the maximum temperature goes beyond the limit. By sending more air, we cool down the stack and we don't let it to be warm up too much, which may cause some problems. So the next question, what's the effect of operating temperature and pre-cracking ratio on the night riding risk that I already mentioned at the cell level? As you can see in here, the night riding issue is a much more problematic thing in the low temperature. The red area shows the area that we have night riding, and in the low temperature, almost half of the stack is affected. But in the high temperature, because cracking happens fast and we don't have too much ammonia penetrate inside the stack, we don't see that much night riding. And based on these results, we need a lot of pre-cracking, around 80 to 90% to be in a safe region for the stack to avoid night riding. I also should mention that our results is in line with the experimental data that Elcogen company reported in the EFCF conference, and they also observed that they need around 85-90% of the pre-cracking to operate at the safe region, which is in line with our results that we obtained here. So after all of these levels, material level, cell level, stack level, we want to really build a system to use ammonia as a fuel cell in SOFC systems. So how to do that? How to design our system to operate on ammonia? So in here we used a multi-scale, multi-physics approach that we have developed in DTU Energy. And in this approach, we combine all of the levels in a single model in a console, and it provides a more realistic information for us, for example, for cracking, stack operation, and other things. And we transferred it to the system level that we implemented other parts of the system, such as compressor, different heat exchangers, and we want to see how to design a durable and efficient system for this kind of fuel. So in here you can see different configuration that we have designed for this system. The configuration 1, which is the simplest one, which we don't have any pre-cracker, we don't have any recirculation. The configuration 2, which we have an external cracker, as I mentioned, to reduce this night riding risk. The configuration 3, that we have only this recirculation. We also have a condenser to remove the steam content before sending it to the stack again. And configuration 4, which is the most complicated configuration, which has the recirculation and also the external pre-cracking. So in this slide, you can see what's the effect of different designs on the system performance. So this figure shows, as I also previously mentioned, we need a high ratio of the pre-cracking to avoid night riding, maybe around 80 to 90%. So we must have some kind of pre-cracker for the current technology that we have, unless we use some kind of novel things to coat some of the steel parts, or we use new cells to avoid this night riding. But for current technology, we must have a pre-cracker outside the stack. In this table, you can see how different recirculation rates affects the efficiency of the system. As you can see, by increasing the recirculation, we can increase our efficiency considerably, and we reach very high levels of the efficiency. So we also need this kind of recirculation to improve the performance. So by these analyses, we find out that the configuration 4, which has both pre-cracking and recirculation, is the selected one. And we must implement this kind of things in the final system. So the conclusion and the closing remarks is that what was the problem and how to solve it. As I mentioned, and as we saw in our experiments, night riding is a bottleneck for this kind of technology, especially at low temperature. 600, 650, 700. To solve this problem, we should choose a high temperature stack, 800, 850 Celsius. Not all of the stacks can handle this kind of temperature. So we should really think about what kind of stack technology we want to use for this one. The second solution is to implement an external cracker for partial cracking of the ammonia at low temperature and then send the pre-cracked ammonia to the stack to avoid nitriding. We can also do some other novel activities for the low temperatures, such as using some internal cracking inside the manifolds, using counterflow distribution, and we can use some interconnect coating, which all of them are some research questions and they're under development. Thanks for your attention.